I wanted to know if I could predict how an aircraft wing behaves using nothing more than a few equations and Python. So I decided to build my own aerodynamic calculator. It takes an airfoil, an angle of attack, velocity, air density, and wing area, and tries to calculate something that actually matters: lift, drag, and lift to drag ratio. But there's a one problem. I had no idea whether my model is actually correct. So after building it, I decided to challenge it against XFLR5, and the results were not exactly what I expected. Most of us learn aerodynamics through equations. You learn about angle of attack, lift coefficient, drag coefficient. Then I see these equations on paper and think, okay, but what happened if I actually turn all of this into a working program? That's what I wanted to find out. And I didn't want to just make a calculator that spits out one number. I wanted it to actually show how an airfoil behaves as an angle of attack changes. And then I wanted to compare my prediction with an actual aerodynamic analysis tool. So I gave myself a simple target: NACA 2412, Python, and one question: can a simple aerodynamic model actually predict the reality? Before writing any code, I needed to understand what I was actually modeling. The airfoil I'm using is NACA 2412. The first number represents the maximum chamber, the second tells us where the maximum chamber occurs, and the final two digits represent the maximum thickness. So this isn't just a random shape, it is a defined aerodynamic geometry. And the variable I'm most interested in is angle of attack. Basically, the angle between the airfoil and the incoming airflow. Change the angle and the aerodynamic forces change. First thing I needed was lift coefficient. For this simplified model, I'm using the thin airflow relationship. The important detail here is the alpha has to be in radians. So my first job was extremely simple. Take the angle in degrees, convert it into radians, and calculate coefficient of lift. And this is the first moment where the project stopped being just a theory. I could type in any angle, the Python would give me the lift coefficient. For example, at 5 degrees, I get approximately 0.55. It's a tiny number, but that number is about to become an actual force. So now my program needs 4 things: air density, velocity, wing area, and the lift coefficient. I just calculated. I put those in Python, and now instead of saying this airflow has a CL of 0.55, my program can say this wing is producing approximately X newtons of lift. That's when this started feeling like an actual engineering tool. But an aircraft doesn't just produce lift, it also produces something that is much less helpful, which is drag. For this project, I'm using a simplified drag polar. Again, this isn't a universal equation that perfectly describes every aircraft. It's an empirical approximation, but it's good enough for the first version of my model. So I added drift coefficient, then used the formula to calculate drag, and finally lift to drag ratio. Now the calculator could tell me 3 things: lift, drag, lift to drag ratio, and that meant I could finally start experimenting. Instead of calculating one angle, I made Python calculate the lift coefficient from -5 degrees all the way to 20 degrees. Then I plotted it. And this was the first graph my program produced. This is basically the moment I wanted, because now I'm not just looking at an equation, I'm looking at aerodynamic behavior. As the angle of attack increases, the lift coefficient increases approximately linearly in this simplified model. But here's the problem. Real airfoils don't just keep increasing lift forever, eventually they stall. And my simple equation doesn't magically understand all the complicated physics that happens near stall. So already I knew my model had some limitations, but I wanted to know just how big those limitations were. At this point, I had a working model, but I had a problem. How do I know if it's actually right? I could look at my graph and say, yeah, that looks aerodynamic. But that's not validation, so I needed something to compare it against. That's when I opened XFLR5. XFLR5 is an aerodynamic analysis tool that can analyze airflows and wings, so I set up the same airfoil, NACA 2412, and generated its aerodynamic data. Now I had 2 models. One was mine, and the other was dedicated aerodynamic analysis tool. And I wanted to see how close they were. I exported the data, put the result together and plotted them on the same graph. At first I was looking for one thing: do the curve overlap? And not perfectly, especially as the angle of attack increases, the difference becomes more obvious. And honestly, my first thought was, oh no, my code is wrong. But then I went back to the assumptions. My model is deliberately simple. I'm using thin airfoil theory. I'm using an empirical drag polar, and I'm treating the relationship in a simplified way. XFLR5, on the other hand, is doing much more involved aerodynamic analysis. So the difference wasn't necessarily evidence that Python has failed, it was showing me something much more interesting: the limitations of the model. This is actually one of the most important things I learned from the project. An equation can be complicated usefully without being universally accurate. A model is only as good as the assumptions behind it. So, did my aerodynamic calculator fail? Honestly, no, because the goal was never to recreate the professional aerodynamics solver from scratch. The goal was to take something I had learned theoretically, turn into code, and then test whether my assumptions survived contact with more sophisticated model. And they didn't survive perfectly, which is actually what made this project useful, because now I know what I needed to improve. I could add Reynolds number, I could make the NECA airflow input automatically determine its geometry. I could compare multiple airfoils. I could separate profile and induced drag. I could eventually move from a simple two-dimensional airfoil model towards a three-dimensional wing model. And that's where this tiny Python project starts becoming something much bigger. I started this project with the basic one question: can I turn the equation I've learned in aerodynamics into something that actually does something? And the answer is yes. But I also learned something I didn't expect. The interesting part of engineering isn't just getting an answer, it's understanding why you got that answer, when it stops being valid, and what you need to change to make it more better. So, this isn't a professional aerodynamic simulator. It's my first attempt to building one, and I think that's more interesting because this is how engineering starts. You take what you want, you build something, you taste it, you break it, and then you build it again.